So in the first module, we discussed the basics of GIS, what it can be used for, and a little bit about the different data types that we use in GIS analysis. And we discussed particularly two data models, the raster data model and the vector data model. And the second and third modules, what we're going to do is discuss each one of these in a little bit more detail. So I'm going to begin with just going over the basics and some of the things we can use raster data for here. So raster data, as I hope you remember, are data that are based on pixels. So if we zoom in far enough on a raster data layer, we eventually see the individual pixels making up that image. We can't zoom in any further onto those pixels. They're always going to be a set amount of data. Just like what we see in this image here, we zoom in far enough on Notre Dame campus, we see the individual pixels of the image. And the size of those pixels in real-world coordinates is something we refer to as the spatial resolution. So it's the length of one side of that pixel in real-world coordinates is what we call the resolution. So if it's 10 meters on a side, we call it a 10-meter resolution image. And that 10-meter resolution image means that each individual pixel covers 100 square meters. If it was 5-meter resolution, it would be 25 square meters. If it was 1-meter resolution, it would be 1 square meter. Now, if we want to see what this looks like across different data types, across different resolution imagery, we can see that in this image here, where we have something that has 30-meter resolution. We can barely make out the details of Notre Dame campus here. Whereas we get through 10-meter resolution down to 60-centimeter resolution, we begin to see a lot more detail in the individual image. And just to show these in a slightly different way, as we zoom in on one image, we begin to lose these details. We begin to see the individual pixels in there. And I've already mentioned a few times that we can't get in any further. And that's just the nature of pixel-based imagery, is you can't really enhance them very much beyond the individual pixel without asking for some sort of outside data that really isn't present in the initial image. But let's look a little bit about the basics of what this imagery is. At its heart, essentially what we're looking at is a matrix of intensity values, of how bright to display an individual pixel. We can think about this just like we would a matrix of numbers, because that's essentially what it is. It's a big matrix of numbers that the computer then uses to display that particular pixel in how bright it is, and even in how colorful it is. So if we want to look at these values, what we can see is one image on the left here, and then the individual values of those pixels on the right. Now, just like we would be able to with any other matrix of numbers, we can begin to do some matrix algebra and some different types of filters on it that allow us to see some sort of neat things from raster data. So just to review a little bit on the properties of a raster, each grid cell holds a value. It might be 5, it might be 3.6, it might be blue. And then that value controls how the computer displays that particular spot. So it can be, the cell can hold an index. It could hold, say, 1, which we could translate to water, 2 would be forest, something like that. It can be a scaled value, something like elevation, or it can be the amount of light reflected. And this is what a digital photograph is it's essentially the amount of light reflected back at the image. So the resolution is then the size on the ground, so that's how it scales that matrix of numbers to be sort of real-world coordinates. Now, the most common and the most basic type of imagery that we deal with is what we call 8-bit imagery. And this is a grayscale image, so an image that's only in black and white, where each cell has a value from 0 to 255, so 256 possible values. Now, for the people out there that are sort of mathy, 256 is 2 to the 8. 2 to the 8th power. This is why we get 8-bit imagery out of it. So each cell has a value that then corresponds to that color. So a low value is going to be very dark, a high value is going to be very light. And we can think about this as sort of being scaled in the amount of color. So the difference between 252 and 253, our eyes can't really pick up that difference. But the computer can, and these small differences are meaningful in some cases. So we want to make sure that we understand that even with 256 possible values, there are things beyond the ability of our eyes to pick them out. Now, the neat thing about this is we can begin to calculate some statistics on an image just by looking at all the values that make up that matrix of numbers. And the most common thing that happens is we put these into a histogram. And this histogram lets us understand something about the image. So in this really, really simple basic one that I've been using as an example, you can see that if we look at the histogram, we see that there's an overwhelming preponderance of really light pixels. That's all that white area that's in there. There's a little bit less that's very dark, and there's kind of a little bit of a bell curve-ish thing in the middle there. That's all those gray values that we see. So from these histograms, we can begin to do things like create a little bit of an understanding of what the mean value might be, the standard deviation, any number of other kind of basic things that let us understand something about the image. Now, if we look at this for a much more complicated image or a bigger image with a higher spatial resolution, you can begin to see that we have essentially the pixel values across the x-axis here, and then the number of pixels falling into each one of those bins, or falling into each one of those values across the y-axis. So what we begin to see on this image is it looks like we have something that's quite dark, a section that's quite dark, and then a whole lot that's kind of falling into this sort of less than 120 but more than probably 60 range. And almost nothing in the image that's very, very bright. And this is common when we deal with sort of things coming from different remote sensing techniques or things coming from different types of imagery sources. And this is what this image might look like, or an image like this might look like, where we have kind of a histogram. Most things are sort of dark in there, and what we end up with is an image where we can't really see a whole lot of detail in there. And even worse, what often happens is we get something that looks like this, where we have almost no detail that's visible, and if we look at the histogram, almost everything is sort of falling within one little value where our eyes can't really pick out the differences there. Now, what's really useful about a histogram is we can do something systematic to it to sort of stretch out the differences and begin to see those things in a way that our eyes can pick them out. And that's what we call a stretch, a histogram stretch. And in this case, what we call a linear histogram stretch. So essentially what we're doing is we're taking the value that was previously 127, sort of the maximum value in that really, really restrained histogram, stretching that out so that it becomes the maximum value, 255, and then displaying what the resulting image might look like. So we begin to see things that was previously, say 60, has now become 80, but what was previously 59 has now become 70. So we actually can begin to see the differences between these things in a way that we couldn't previously. So we can actually do the same thing with the low value as well. So it was previously sort of in that gray area, maybe 100 or so, has now been stretched out to be a much lower value. So what we've actually done is we've created something that looks more like a normal curve, more like a bell curve, and begins to show us some of the differences in the image much more clearly. So this is that linear unstretched one. This means that there's no stretch applied to it. It's that image we saw from the very beginning where we just have this sort of everything falling into this one little section. And this is what it looks like when we begin to apply these standard stretches to them. Now, a standard deviation stretch, like what it says up here, is essentially taking the mean value, going out 2 standard deviations, that becomes the maximum, going 2 standard deviations in the other way, that becomes the minimum. So it's a systematic way to apply these. And these are so common with remote sensing data, with satellite imagery, with any sort of imagery that we're going to deal with in a GIS context, that it's the default when you load something into the software we're working with, is that it has these stretches on it. There are other ones we can do that are more complicated, and this is one's called a histogram equalize. We'll talk about this a little bit more in the demonstration part of this module, but the histogram equalize is essentially not doing a linear relationship, so it's trying to put everything into enough bins that we have a very pretty bell curve in there. So what about color imagery? How is color imagery different? We've been dealing with black and white, what we call grayscale imagery, and we don't really take a lot of color photographs anymore, so this might be a little hard to think about. But color imagery is essentially the same thing, just repeated multiple times. It's really common that we see color imagery from satellite sources. Most of our raster data is going to be color in some way or another. And essentially what we can think about this is because the computer makes up color by combining 3 different types of light, we can do the same thing when we build these images in a GIS context as well. So computer screen, everything is made up of red, green, and blue light. Any combination that you're seeing has some value for red, some intensity value that's displaying that color for red, intensity value for green, intensity value for blue. This is what they kind of look like. So we have an image here where we're seeing sort of a yellow construction equipment with a blue sky and a few other things in there. And you can see that the computer at its heart has 3 different layers in there. It has a red layer, a green layer, and a blue layer. And it's sort of the intensity of red, the intensity of green, and the intensity of blue combined together is how it creates all the different colors. And this is essentially, you can do this in Photoshop, you can do this in pretty much any image manipulation program. You can play with these different things. And you can do the exact same stuff in GIS. So what we have, if we're looking at a particular type of imagery here, in this case this is Landsat, it's a type of satellite imagery. We'll get to this much more in a later module. We might have 3 different bands of sensors that we've gotten from the satellite. And we can combine them together in the same way. So we have band 1, band 2, and band 3. Each one goes into a particular color channel or gun. Sometimes you hear them called channels, sometimes you hear them called guns. It's essentially just the way what that particular data is being displayed color-wise as. So we can combine them into our red, green, and blue. And then we can mold those together into one image that shows us all 3 of those different layers at once. So in this case, green, red, and blue are bands 1, 2, and 3. So what are the advantages and disadvantages of our raster data model before we begin to look a little bit more at some of the different data sources we might deal with? The advantages are it's continuous, it's a grid of numbers, it's a matrix of numbers, so it's got to be continuous across the entire area that you have. It may be that there are certain areas that we sort of flag as no data or we don't know, but there always is data for each pixel in a raster image. We can perceive detail well beyond what our eyes can. Again, that's why these stretches work, is we can't see the difference between a 78 and a 79, but the computer can, and we can begin to manipulate it so that that actually makes it a little bit more clear. It's very easy to manipulate raster data like this. We saw that from the stretches. Those happen lightning fast. Some of the disadvantages, perhaps, we have a fixed resolution. Well, we can't get in any further than the resolution that we have the image at originally. It's just simply not possible. Because they're continuous, we tend to have very large file sizes on raster data, and it can be kind of difficult to go in and edit individual pixels. So let's turn a little bit to talk about some of the things we can do with these raster data. And probably the most common one that we deal with is satellite imagery or remote sensing data. So before we get into too much about satellite imagery, I just want to make sure that everyone understands what makes a particular object a particular color. It's essentially how much light is reflected of that color off of the object. So a red object is actually reflecting red light back at you and absorbing all the other different wavelengths of light. So this is the same thing is even true in wavelengths of light that we can't see. And because particular objects reflect differently in different wavelengths of light, so this is actually the same is even true in wavelengths we can't see across the entirety of the electromagnetic spectrum. Whether it be the little tiny section in here that is visible light that we can see, whether it be the ultraviolet, whether it be the near infrared. Different objects, different types of cover, different things absorb particular wavelengths of light and reflect other ones back at you. We'll get into this a lot more in a later module on satellite imagery analysis, but I just want to make sure that we can get through the basics of this so we can understand the raster data that we're going to be manipulating in the demos for this particular module. So because each object reflects different wavelengths of light in different ways, we can create what's called a spatial or spectral reflectance curve. And a spectral reflectance curve is essentially starting at a particular spot in the electromagnetic spectrum, working our way up, how much light, what percentage of light is reflected in different wavelengths. So again, an object that's going to be red is going to reflect very, very strongly in the red, and it might absorb all the other colors. But this is even true in areas of the spectrum, of the electromagnetic spectrum that we can't see, like the near infrared. And the near infrared is probably the most useful one for satellite imagery analysis. Now I want to make it clear here when I'm talking about near infrared, this is not predator vision. This is not infrared cameras and things like that. This is a wavelength of light that's somewhere in between there, and it lets us see some different things. You can notice this a little bit from the spectral reflectance curves that I have up here, which show bare soil, which is kind of grayish brown, vegetation, which I have in green, and then water, which is generally kind of clear, maybe with a little bit of a bluish or greenish tinge to it. So this is the section that we see as visible light. And you begin to see pretty quickly why trees are green. There's a little hump right there in the green spectrum. You begin to see why water is kind of bluish green. There's a little hump right there. And why other things tend to be lighter in general. They reflect more light overall. Now, if we're looking at a black and white image, a grayscale image, this is what we would see. The sort of mean value across this entire area controls what is light and what is dark. So water is going to be really dark. Trees are going to be something in between. Bare soil is going to be a lot lighter. And that's exactly what we might see in something like this, where we see pavement, bare soil tends to be quite light, the river in there tends to be very, very dark, and everything else is somewhere in between. Now, if we do that thing where we're putting individual wavelengths, individual bands in the different channels or guns to see a color image, well, this is what we would do if we wanted a real color image. We'd put the blue reflectivity in the blue band into the blue gun, and reflectivity in the green band into the green gun, and reflectivity in the red band into the red gun. And that's how we make a color image. That's why we begin to see these colors sort of recreated on the screen like this. But if you look out on that band, on that spectral reflectance curve, there's lots of sections in there that reflect things that we can't see. They're well outside of the visible spectrum that seem to be doing some pretty interesting stuff. Vegetation starts reflecting almost everything when we get out of the visible spectrum. Water starts absorbing almost everything and reflecting almost nothing. And soil kind of doesn't do much all that different. It sort of gradually increases. So let's look at this one little section right here, where we see that instead of vegetation having absorbed or reflected less light than vegetation or than bare soil, it's now flipped. So it's actually reflecting quite a bit more. So things that are vegetated should be brighter than things that are not vegetated at this point. And that's exactly what we see. As we see the sort of crop fields in here are a little bit brighter than water, than cities, than things like this. And it's this near infrared band that lets us figure out some really, really neat environmental things from remote sensing data. And very commonly what we end up doing is being able to see everything, being able to see multiple stuff at the same time. There's not a lot in nature that's particularly red. So what we might want to do is, instead of showing the red gun, that red channel showing red, we might want to have it show near infrared. That's exactly what we have here. So we're showing the blue is still blue, green is still green, but we're not showing anything that's red. We're showing a different wavelength of light in the red gun. And this is a really common way to see satellite imagery, where things that are more red are generally more vegetated, or at least reflecting more strongly in the near infrared. We're going to deal with how to manipulate these things a little bit in the demo today. But really all of the same stretches, all of the same things that we did on single band data, we can do on these multi-band data. We just have the advantage of being able to put different wavelengths of light, different things into different guns, and be able to see stuff that's well outside of our ability to see with our naked eyes. Now there's one last little part of analyzing these data that I want to talk about. And it has to do a lot with the fact that these are matrices of numbers again. So really the difference here between our single band images and our multi-band images, so our black and white images and our color images, are two kind of key terms that I want to make sure that you guys understand well before we get to the point in the modules that it's extremely important. And that's the difference between these two types of data. So we have our panchromatic image. Panchromatic means covers multiple chroma, or multiple colors, multiple sections of the visible spectrum. A black and white image, essentially. An image that we just show in a single black to white color ramp, and really is reflecting reflectivity or sampling reflectivity across the entire visible spectrum, and maybe even a little bit beyond. And then we have our multi-band images, which are essentially a color image. We're putting individual slices of light, individual reflectivity, and individual wavelengths into different color guns, and then using that to recreate different colors. Now, regardless of which one we're dealing with, there are a few different other things that we can sort of marshal the fact that these are matrices of numbers. It might be 3, 5, 7 matrices stacked on top of each other, but they're matrices of numbers that we can begin to do some different types of analysis on. Now, the first concept in here that's important is what we call spatial frequency. And this is essentially the difference between pixels, the kind of mean value of differences between pixels. So something with 0 spatial frequency is all the same across the entire thing. If we took an image of blue just for the ocean, or image of green just for the Amazon, it would have very low spatial frequency. It would all be basically the same across there. If we had something with a very low spatial frequency, it means it kind of gradually fades from one thing into another. You can see in that middle image up here where it sort of goes from black to white very, very slowly and gradually. Whereas something with very high spatial frequency is very different between individual pixels. So we might have something that's black in one pixel, white in another, and goes all the way across like this sort of checkerboard pattern here. Now, when we're analyzing the spatial frequency, when we're doing these different types of things, the best way to understand these is to do something we call a filter or sort of a manipulation of the image that we do by looking at an individual pixel in relation to the pixels around it. And what this lets us do is understand things related to the spatial frequency, because we can't really understand what the spatial frequency is just by looking at an individual pixel. We also have to look at the ones around it. So what we're seeing here is if we're looking at an individual pixel, we're applying some function to it based on the values around it, and then we're modifying the original pixel value based on the stuff around it. And this local neighborhood is something that we call the kernel. So this is the area of pixels contributing to the new value. And essentially when we're doing these filtering techniques, what we call convolution filtering, we're looking at one pixel, looking at all the stuff around it, and then moving on to the next one and looking at all the stuff around it. And only the old values. So we're going to have an old layer and then a new layer, and that filter has been run on. And the kernel will the path will sort of move across like this in a very systematic way. So the way that these convolution filters work is by essentially we have our kernel, what we see up here with all these -1s and a 16 in the middle. And the way that they work is we multiply each value from the original image by its value in the kernel. So the center one is multiplied by 16, all of the others are multiplied by -1. We create the sum of all of these values, and then we divide it by the sum of the filter itself. Now this is complicated math and probably a little bit difficult to wrap your head around, but it lets us begin to see some sort of neat things in the image. And we'll do these a lot in the demo for this particular module. So we might have something like what we call a high-pass filter. What we see here is this is the exact one I was using in the demonstration in the previous slide, where we have our original values and then we have our new values that we've created by multiplying there. So we've taken -8 or -1 and multiplied by 8, -1 multiplied it by 6, -1 multiplied by 6, all the way across. The center one's the only one that's different. That's going to be 16 times 8. And then we're going to sum all of those values together, which is going to give us 128. We're going to divide that by the sum of the kernel, and that's going to give us a new value of 11. What this is doing is essentially it's increasing differences based on the spatial frequency. So if it's very different in there, it's going to get a higher value. So in this case, we have 8, we have 2, we have 2, we have low values and a high value in the center. So it's actually quite a bit different there. There's a high spatial frequency between this pixel and all the ones around it, with a couple of exceptions. So there's a moderate, perhaps. So it's going to increase that to be 11. If they were all the same, it would actually decrease it down. So if all the values around it were 8, it would end up just being 8, even if the center one was different. So this sharpens an image. So this is what happens if we apply our high-pass filter. As it goes through in any place where there's a little bit of difference, it makes it a bigger difference. So we begin to see very, very different areas in there. And we can pick out some things that we might not have been able to see with our naked eyes. Now the contrast to this is what we call a low-pass filter, which is essentially going to decrease the frequency, the spatial frequency. So if we look in there, I'm not going to walk it all the way through again, but essentially what you see is that instead of increasing the value of 8 to 11, it's actually decreased it. So it's actually sort of blurring things out and making it so that there's less difference in there. So we're actually going to see something that looks like this, where it was larger differences before, and now it's much, much blurrier. There seems to be a lot less difference in there. Now, a frequent question when I show these low-pass filters is why would you ever do that? Why would you decrease your image? Why would you blur out your image? It's really useful if there's noise in the image. If you're taking something from a remote sensing technique or something where there's actually noise in there, where there's a problem with the sensor, it's a way to kind of overcome that pretty well. There are other ones, things that we call edge detect filters, that are going to go through and either vertically or horizontally or sort of diagonal. We'll see if there's a big difference from one side to the other, it'll give it a high value. If there's no difference, it'll give it a very, very low value. So what you see here is from the middle image is the original, and the one on the left is a vertical edge detect. So anything that's very, very different in east-west is going to be white, and anything that's not very different in east-west is going to be black. And the other one is a horizontal, so anything that's very different north-south is going to be very white, and anything that's not very different is going to be black. So that's really it for talking about for convolution filtering and ways that we might begin to analyze some of these raster data. In the demonstration this week, we'll deal with these techniques in a lot more detail.